On the test, do not put on dot, dot, dot. You really have to figure out the work and then show me the answer, right? So which integration technique do we use? Of course, this is the hardest question whenever we need to solve an integral. So in this video, I would like to demonstrate certain examples on what the things I'll be looking for when I am solving an integral. And in fact, all these examples, we have done it already, but it's just that, you know, I have the integration by parts video. In that video, we just do all integration by parts. I have a trig sub video, we just do all trig sub, right? So this is like the collection of like random integrals, and we'll see how to attack that. Hopefully I can give you guys some insight, and definitely try the questions first before you watch the solutions. The link to the PDF will be in the description for your convenience. So I would like to start off by telling you guys that we should always do the easy ones first. Maybe easy in terms of like you know what to do, right? You know what to do right away. I think that would be easy, because if you look at this 4, perhaps the easiest one is this, because we know what to do, because we have a rational function 3x minus 5 over x minus 1 times x minus 3 times x minus 5. So we know we should use partial fractions, right? So I'll just say we use PFD, partial fractions decomposition. And let's also talk about the setup, because that's the most important step. So let's write down 3x minus 5 over, and the denominator is nicely factored for us already, and the degree on the top is less than the degree on the bottom. So the breakdown is going to be this for the first denominator, and the top will be just a constant because this is linear, and this right here will be 1 degree less than that. And the next one is x minus 3 with a constant b on the top, and then the last one is that denominator, which is x minus 5 and then c on the top. And right here, this is actually really nice because we can use the cover-up method for solving a, b, and c. Alright? So again, that would be my insight, right? That's the first step. And I'm not going to work out the whole solutions because again, you guys can watch my other videos for them. So let's continue. Which one do you think is the next easiest one that we have on the board? And again, we have like another 9 besides this. But I will say maybe this one, because you see that we have 2 terms inside raised to the second power. Let's do some algebra first. Let's multiply things out. When we do that, this is the integral, and we just have this thing squared, which is sine square x, and then we add it with 2 times this and that. So we have 2 sine x cosine x, and lastly we have this thing squared, which is plus cosine square x dx. And let me just put down parentheses for you guys. Anyway, right here we see that this and that, it's actually really nice because that's just equal to 1. So we will just have the integral of 1, and then we add it with, well, if you look at this right here, 2 sine x cosine x, this right here is just the double angle identity for sine of 2x. So we can just multiply it out, and that will be the first and also the second step. And you know what? In fact, this right here is actually really nice. So I will finish this one for you guys. Integral of 1 in the x world is just x. Integral of sine is negative cosine, and then the input stays the same. But remember, we will have to divide it by the derivative of this, which is the 2. So we will just multiply by 1 over 2, just like that, and then we're done plus c. Right. So it takes 3 lines to finish that. Okay. Next one. I will say number 1 is easier to know because we have an inverse sine function. What do? Let me tell you, whenever we're trying to integrate an inverse function, most likely integration by parts. But more specifically is that, you see how we just have one thing, right? We have to integrate that. Why don't we change that to differentiation? But we still have to talk about integration. So we are breaking apart. One part to be differentiated, the other part to be integrated. That's integration by parts. And that happens a lot whenever we are dealing with inverse functions. So of course, do the DI. Let's go ahead and differentiate inverse sine x instead, and then we'll just integrate 1. Well, of course, that's the first step, and of course, let's talk about how do we differentiate that. The answer for that is 1 over square root of 1 minus x squared. And this is what you definitely have to remember really well. I have a video on showing you guys how I remember all the derivatives of the trig functions and also the inverse trig functions, so go ahead and check that out. And right here, we'll just integrate 1, which is x. And that's pretty much it for the integration by parts setup, right? And remember, this times this is the first part of the answer, and we multiply these two things and put them inside of an integral. And the truth is, this over that can be integrated by u sub. And just go ahead and finish this on your own. But again, that's what I will do, right, for this particular integral. And that's the reason why. Now, if you take a look at number 4, so how do we do this though? Well, you see that here we have x to the 5th power. The power here is bigger than x to the 3rd power. So maybe we can kind of break it apart. Or maybe we can just try some u sub first. So let's see. Yeah, of course, if you look at this is definitely not partial fractions. This is definitely not trig sub because you have the trig function already, right? So maybe u sub and integration by parts, right? So right here, let's go ahead and perhaps let's do the u sub first. I'm going to say u equal x to the 3rd power. And this is actually really nice. When we differentiate this, we get 3x squared dx, and then of course do the usual business. Dx is equal to du over 3x squared. Take this integral to the u world, we get x to the 5th power here. Well, you can also break it apart like how we talked about earlier. Perhaps let's do that. You see, if we break it apart, this is x to the 3rd power times x squared, and then we have sine of x to the 3rd power dx. And this right here is the u, and this right here is just x squared, and then we have sine, and then x to the 3rd power is again the u, and dx is that, which is du over 3x squared. This is so nice because you see that x squared cancel each other out. So we don't have x in the u world. So that means we're on the right track. Right here, u times sine of u, that's integration by parts, right? When you have u to a positive whole number power times sine or cosine, and then if the input is just u to the 1st power or any linear functions inside, that is integration by parts. So we can see that pretty easily in the u world. So to proceed, I would like to put a 1 over 3 with the u right here. So instead of putting that 1 over 3 all the way on the outside, let's put it together right here, and then we have the sine u, and of course du. And the reason is because right here we can do the di, and then plus, minus. I can just put down this right here to be differentiated. So 1 over 3u, and then this right here is sine u. And of course, we can just proceed. And this is the case that everybody likes, because when we differentiate this once, we get 1/3. And then when we integrate this, we get negative cosine u. And the truth is, we can just go ahead and do it again, so we can get to 0, and then we can stop. Well, remember, plus, minus, plus for the sign on the side. And then when we do this again, we get 0. When we integrate negative cosine, we get negative sine u. And congrats, we pretty much have an answer. This times this is the first part of the answer, and then this times that is the second part of the answer. And then remember to just go back to the x world. So I'm going to let you guys finish that. So if we take a look at these 4 examples, I think I will tell you guys that let's do this one first, because we know what to do. Because we have a rational function, so we use integration by partial fractions. I know partial fractions are long, but the good thing is that once you see an integral that calls out for partial fractions, you just have to do the work, right? It's just the algebra, it's not the integration that gets you. But anyway, we will use partial fractions, so PFD for this. And of course, let's talk about the setup for the partial fractions. And the denominator is once again nicely factored for us, and the degree on the top is less than the degree on the bottom, so we can totally proceed without doing the long division. So this right here, notice we have x plus 2 squared. This means x plus 2 times x plus 2. This is the repeating factor, and then the inside is a linear. So we have to build out the power, right? And then the top stay the same time. Well, we will take care of this first. This is just linear, and we'll just have x plus 1 on the bottom with a constant on the top. For the next one, we will have to build out the power, so we are going to start with x plus 2 to the first power, and because this is linear on the top, again, it's just a constant. And then we are going to go up to the second power. So here we have x plus 2 and then square, and then here we will have a c. So this right here is a setup. And you can imagine if this is a 4, then we just have x plus 2 here, x plus 2 square, x plus 2 to the third power, and then x plus 2 to the fourth power. Yep. But I promise you guys, especially if you're watching me from my calculus class, I will never ask you guys to the fourth power. Maybe the third power. But no, not really. Like the second power, usually that would be the deal. Anyway, yeah. And now, let's make this a little bit simpler. Let's talk about which letters can we use cover up. You see, here we have this denominator, so A we can use cover up. Here we have this denominator, so C we can also use cover up for it. So we can use cover up for A and C. And after we finish A and C, of course, we just put them in and then just multiply everybody by its lowest common denominator. For the B, we just do the go away. So yeah, I'll just say for B, do the OG way, original way, right? Do the OG way. Yeah. Cool. All right, so that takes care of that. I really don't know what you guys think about partial fractions, like integral fractional functions. You like it because you know what to do. You don't like it because you know it's going to be long, right? So anyway. So 5, 6, 7. Maybe let's do number 5, because we see that we just have the square root of x squared plus 1. There's no x on the outside. If we have an x on the outside, then we can just do u sub, because the derivative of x squared plus 1 is 2x, right? But we don't have the x, so u sub is not going to work out so nicely. This right here, x squared plus 1, we can do trig sub. So pay attention to what we have here. We have the sum of 2 squares, so I will just say use trig sub, right? And the trig sub is going to be x is equal to the sum of 2 squares, so we'll just have tangent theta, okay? And don't forget that dx is equal to the derivative of that, which is secant square theta d theta. All right, so that will be it. You plug in and then just kind of work this out. And of course, you will have to use the trig identities here and there. And I'm going to leave that to you guys. All right. So again, we know what to do for that because we have that form right there. So, okay, let's just deal with number 6. The integral of ln over x squared. If we don't have the square, then again we can do u sub. Let u equal ln x, and that will work out nicely. But we do have the square though. And of course, this right here, can we do partial fractions? No, because it has the ln, right? And can we do u sub? Maybe not so much. You could, but it's a little bit longer. But the truth is, right? The truth is, whenever we have an integral of x to some power times ln x, whenever we have an integral in this form, we do integration by parts. So this is a classic integration by parts question. All right. And in fact, this right here is just x to the negative 2 power. So this right here satisfies this. So let's go ahead and put down the d and also the I, plus and minus. And for this case, we will differentiate ln x. And then we'll integrate 1 over x squared. Do not integrate ln x, because if you want to integrate ln x, you have to use integration by parts for that, right? This right here is so much better because you see that the derivative of this is just 1 over x. Integral of this, I'm going to let you guys figure it out. Well, I'll do it for you guys. This right here is the same as x to the negative 2 power. Add 1 to the power, which is negative 1, and divide it by the new power. So we get negative, all right? And then x to the negative 1 power, which is just 1 over x. Yeah. This times this, congratulations, that's the first part of the answer. And multiply these two things together, put that inside of an integral, and don't forget, negative times this negative, right? So it's a plus integral. And 1 over x times 1 over x, that's something that we can integrate. And then I'm going to just leave this to you guys. Go ahead and finish that on your own. And again, just kind of finish this on your own. On the test, do not put on dot, dot, dot. You really have to figure out all the work and then show me the answer, right? I'm just going over the strategies, like the insights with you guys. Okay, this one is rather bizarre. We have an e to the x on the top and okay. No partial fractions, no trig sub. Those are pretty obvious, right? And it has no sine cosine, so no. So perhaps our best bet is by using u sub. And how though? Because we have e to the x on the top, so I think, if we have u in terms of e to the x, then that might work. If we let u equal e to the x, then you see du is just going to be e to the x dx. And this right here will just be on the top, so that's nice. But if e to the x is u, what's this guy? Take a look. This guy right here, let me just rewrite it. This right here is e to the x over 1 plus. This guy, e to the 2x, is nicely equal to e to the x and then square. So in fact, once we look at this integral like that, then the u sub is more obvious, but it might be hard to see at first. So that's why I did this at the end. This is, again, really easy to see, but anyway. Here we have the integral, and if you pair this and that together, that will be the du. So we'll put it down on the side. And then we'll just have 1 over 1 plus, this is u, and then square that, right? And perhaps I'll also finish this one for you guys. What's the integral of 1 over 1 plus u squared? And the same question is, the derivative of what function will give us 1 over 1 plus u squared in the u world? The answer to that is inverse tangent of u. So the answer for that is just inverse tangent of u, but u is equal to the x, so we'll just put that down right here, so that saves us one step. So this right here, it will be the answer for that. And now let's take a look at these 5 integrals. And I think the easiest one to know what to do right away is number 12. Because I see that we have the square root of 2 minus x squared over x squared. Well, unfortunately, u sub wouldn't work, and this is the one of the classic trig sub question. And the first thing that we have to know is this is the difference of this and that. Look at the 2 as square root of 2 squared, right? And again, because right here we are going to use trig sub, and of course I'll tell you guys which trig function to use. When we have a number minus x squared like that, we use sine. So we are going to let x equal the a value is the square root of 2. All right, and then we use sine theta. And right here, of course, do the usual business, differentiate this real quick. The derivative of this is square root of 2 cosine theta d theta. Be really careful. Make sure that you plug in this back here as well. And then again, you will have to use the identity, and I'm going to leave the rest to you guys. Right? So that's that for that. Cool. And then perhaps the next one. Let's do number 9, because we have sine to the third power over cosine. So this is the classic integral of sine and cosine, right? So if we can have a sine factor on the side, or maybe a cosine factor on the side, and maybe just change everything else to the other one, then we can just do u sub. We have cosine x on the bottom, so maybe it's a good idea, well, it is a good idea to break down the sine to the third power. So this right here is going to be integral. Let's look at this as sine square x over cosine x, and then we still need another sine x, right? So let's put it down on the side like so. And that's exactly what I said. We have a sine factor right here. That means we should change this right here in terms of just all cosines. Can we do that? Yes, because when we have sine square x, this right here is nicely equal to 1 minus cosine x square, right here, right? Cosine square x, and then over cosine x, and then right here we have the sine x dx. And then from here, we can just do u sub. Let u equal cosine x, and then du equals negative sine x dx. Be really careful, it's in the negative, right? But I'm going to just leave this to you guys and have you guys finish. So dot, dot, dot. All right, what's next? Maybe this one, because number 9 and number 13, they are just straight integrals. This one deals with tangent and secant. So if you deal with tangent and secant, we have two choices. The first one is, can we put secant squared on the side? And in this case, yes. And the other choice is that, can we put secant x, tangent x on the side? In this case, also yes. In fact, we have two ways to do this. The easier way is, here we have tangent to the first power. Let's bring this together with a secant x. So I'm going to write this down for you guys. I will recommend you guys to do this because it's easier. I'm going to look at secant to the fourth power as secant to the third power x right here. And then of course we also need another one. Altogether we get the secant to the fourth power, right? And don't forget we still have the tangent x and of course the dx. And as you can see, when we have secant x, tangent x dx, we wish to have an expression in terms of secant, which we do, right? So right here, we can just go ahead and do u sub, let u equal secant x, and we see right away, du is just secant x, tangent x, dx. Very nice. And I'm going to leave this to you guys to finish. You pretty much just have to integrate u to the third power in the u world, and u is equal to secant x. So that's the first way. Now, for the second way, I'm not going to recommend you guys to do this because it's a little bit longer, but just for practice purpose. The second way is, we are going to break this down into secant square times secant square. So I am going to put down this tangent x first. And then this right here is what we said, secant square x. And then we also need another secant square x. And then here we have the dx. Right? Sorry about this. But you see that when we have secant square x, we wish to have this part in terms of tangent. And this is doable because this right here we can use the identity. Check this out. I'm just going to have the integral, and here we have tangent x. And this right here is just nicely equal to tangent square x plus 1. All right? And then right here we still have the secant square dx. So right here you can see this is in terms of tangent. And of course, you can also multiply this in, but I'm going to leave that to you guys because right here we can just do u sub, that u equal tangent x, and then this guy is precisely the du because that's the secant square x dx. This one is better. Alright, so now two more questions to go. Let's do this one right here. It's actually pretty easy. I will tell you guys what the answer is. If you remember the derivative or the integral of an exponential function where the base is not e, then this is just the formula way to do it. The answer for this right here, because we're doing integral, okay, is still pi to the x, but we will divide it by ln of the base. So we'll just have 1 over ln pi. And then let me tell you, we are done, plus c. Yeah, just like that. So I will just tell you guys the notes right here. When we are integrating b to the x power, this right here is just going to be b to the x, and then we do 1 over ln b like this, and then we are all done, plus c. Yeah. Because the derivative of b to the x is b to the x times ln b, but when we do the integral, we divide it by ln b. So that's it. Yeah, that's it. It just looks slightly more intimidating. I usually like to tell my students that pi is usually more famous in math in general, but in calculus, E is perhaps more famous. Alright, let's go ahead and finish the last one. Let's go through the list, yeah? This right here is not so obvious, but can we do partial fractions for this? No, because we have the square root, right? Can we do trig sub? I don't think so. Integration by parts? Maybe not, right? So usually those are the things that I test out, and usually you can see right away if they work or not. But here, perhaps let's just go ahead and do a U sub, and I can only tell you, let's hope for the best. Let's go ahead and let U equal the denominator, which is 1 minus square root of x. And here, because we have to get the dx by itself, it's actually easier to isolate the x first. So let me move this there, and then let me move the u here, so we get square root of x equals 1 minus u. And then let's square both sides, so x equals parentheses 1 minus u squared. And then we can do the derivative. Dx is equal to, of course, bring the power to the front, minus 1, so we get 2 parentheses 1 minus u to the first power, and don't forget the chain rule, multiplied by the derivative of the inside, which is negative 1, so we need the negative right here, and then we have the du. And if you plug everything in, you can see that this right here becomes the integral 1 over u, and then dx is all that, which is negative 2. Perhaps let's distribute this right here. Negative 2 plus 2u in the u world, right? That's what we have. And the good thing is that we can also distribute the 1 over u inside. So we get the integral of this and that, which is negative 2 over u. And then when we do this times that, the u cancel, so we just get plus 2. Hey, very nice, right? And then we are in the u world. And you see, this is why I don't really like to put the parentheses, because the integral and the parentheses, when they are next to each other, they just don't look that nice. But anyway, I will stop complaining. There. Yeah, so go ahead and finish this. It's not so bad after a year, and I'm about to run out of space, so you finish this. Alright, so certain integrals, we are went over what I will be looking for when we want to integrate that. And sometimes it's easy, sometimes it's not so obvious, then you just have to try it. Alright, so hopefully this helped. If you guys need more help, you guys can check out my other videos. If you want to see the solutions for this, again, check out my other videos for it. If you have any questions, leave them down below in the comment. I will see you guys in my other videos. And as always, that's it.